Hey calculus, we are going to find the volume of a solid using the disk method. So the first thing we do is we take our function y is equal to x to the 1/3 and we graph it. All right, and we're going to take this and we're going to rotate it around the x-axis. So here is the graph. Here is our region. You always want to put in a rectangle. Okay, and your rectangle is always perpendicular to the axis of rotation. Okay, so when you spin this graph around the x-axis, it looks like this three-dimensional solid. It's called a paraboloid. And what happens to this rectangle, as you can see, is the rectangle becomes a disk. And we can find the volume of the disk, and then we can use an integral to sum all of the disks from our left endpoint 0 to our right endpoint 8. So let's go back to our original rectangle right here. That is a vertical rectangle because it's perpendicular to the x-axis. So vertical is a y value. All right, so if you look, this original rectangle right here becomes the radius of the disk. So our radius is a y value. All right, so we go down here. When you're rotating it around the x-axis, the radius of the disk is a y value. All right, so now we're going to find the volume of this disk. Remember from geometry, the volume of a disk is area of the base times the height. We're right down here, area of the base times the height. So the area of the base is a circle. The area of a circle is pi r squared. We're going to change the radius, the r, to a y. All right, so that is going to become pi y squared. All right, so that is the area of the base right here. Now, for the height is the thickness of the disk. All right, so I'm going to try to show you that right here. Remember, the height is always the distance between the bases. All right, so the distance between the circles on that disk is right here. That is the height. All right. Okay, again, the height is the distance between the bases. Because the bases of a disk are a circle, the height is that distance right here between the circles. Because that is a horizontal length, that is a change in x. That is a dx. So the dx is our height. So right here for the height, we put in our dx. So our height is right here, dx. All right, again, this is the area of the base because the base is a circle. And then dx is our height. Let's make sure we fill in this up here. We always want to draw in a rectangle that is perpendicular to the axis of rotation. Now we can complete our integrand for our definite integral. So we have the elongated s, the pi comes along for the ride, but the y value, we can fill in y right here. We know what y is equal to. We go up here to our function. Y is equal to x to the 1/3. So I plug that in right here. X to the 1/3. And then I bring my dx down. And now I have my integral all with one variable. X's and dx's. Pi x to the 1/3 squared dx. Now let's simplify our integrand. So in order to do that, we just have to simplify the exponents. The pi comes along. In the algebra world, if we're raising one power to another, we multiply. So that becomes x to the 2/3 dx. And there's our integrand. Now we can add in our limits of integration. The left endpoint is 0. The right endpoint is 8. Now we can solve this using the fundamental theorem of calculus. So if you remember, the first step is we find our antiderivative. So that pi comes along for the ride. We're going to use the power rule to take the antiderivative of x to the 2/3. So that becomes x to the 5/3. If we add 1 to the exponent, 2/3 plus 3/3 gives us x to the 5/3. And we put the same number on the bottom. And then we use our brackets to bring along our limits of integration, because the notation, the elongated s and the dx drop out once you've taken that antiderivative. Now let's simplify our antiderivative. We don't want to leave a fraction in a fraction, so we need to multiply by the reciprocal. So the pi comes along for the ride. Instead of dividing by 5/3, we are going to multiply by 3/5. So 3/5 x to the 5/3 from 0 to 8. There is our antiderivative. Now we simply find the value for 8. We plug 8 into our antiderivative, we plug 0 into our antiderivative, and we subtract. All right, so pull out your calculators, put the antiderivative, pi times 3/5 x to the 5/3 into y equals, and use your table to find these two values. Do that right now. I got 60.32 when I plugged in 8, and obviously when you plug in 0, you get 0. So our volume is 60.32, and that's units cubed for volume. So there is an example of a disk problem rotating it around the x-axis. So let's review. When we rotate along the x-axis, here's what we keep in mind. We want a vertical rectangle because it has to be perpendicular to that x-axis. So here is our rectangle. All right, here it's a vertical rectangle, so our radius is y. All right, but the thickness is a horizontal length. So that is a difference in x. All right, so your height is a dx. All righty, the second thing that we want to keep in mind is our limits, a and b, are along the x-axis. Everything matches in volume. If you're rotating it around the x-axis, your limits are along the x-axis. So let's just go up to the graph and just verify that. Our limits are along the x-axis from left, 0, all the way out to 8. The limits are along the x-axis. All right, so that's the second thing to keep in mind. And then third, your definite integral will always be x's and dx's. All right, so it will be x and dx. The function is the area of the base, which is a circle. So the area of a circle gives us pi y squared, and then the height is dx. And then we always remember to plug in y. All right, there you go. There's our first disk problem.